one generator, one bus.
Yeah.
So think of this, none of this exists for you. This generator is just stuck here and then you have a bunch of loads. That's it. And then depending on the case, they literally tell you what button to press and you just run it.
Okay, I must just click on it.
So just download a bunch of cases and look what lines up with your class.
A ton of them.
Yeah.
Okay.
What works best with your class. And honestly, what I ended up doing is like deleting stuff that I didn't need. Move this guy over, stick it, and then, so that's the draw if you really want to draw it. And then you have solution details. I believe it's here that you find 3 different ones, and you just click the one that you need, right?
Thank you.
Was it Newton-Raphson or? Gaussian?
Single solution full Newton.
Okay, yeah.
Yes, and it's a hint for the whole.
Okay, I just did.
Just one
Cases.
line.
I still have a few minutes, so.
Yeah, right here, so it's.
So I was just looking through my old,
Oh.
what I discussed during day 1, and I promised that there is a website that you can go and look at more or less all the salaries in US. So this is a do.gov website, and if you scroll down somewhere here, I actually downloaded this last night for my own sake. So this is for 2024 quarter 1. So anything and everything up to April, no, March 31st. And I'll just show you the. I think it's about right. So it's a pretty long, I think it's several 50,000 is the count that I saw. Oh, sorry, it's more, even more than that. So around 70,000 actual salaries to the cent are being shown here in this website. Your job is, it's a huge spreadsheet. So W is where you will find all the name of the company. I just like to see the title. And then I am kind of interested in what exactly is the job, the qualification that's required for the job. So for example, office clerk, none. Some sort of an inspector, high school is required, energy auditor, bachelor's. And then this is how long they were with the company, is my assumption. And if you scroll a bit further, you should start seeing the salary. So take some time, go through this. So let me see if I can, any favorite companies that I should be looking at? From Oregon? Sorry?
Jacobs might be on there.
Let's see. Most likely they don't file. This happened.
Control that.
Is it Jacobs?
Yeah,
Let's see.
engineering, yeah, Jacobs engineering,
Oh, yeah.
yeah.
Is Burns McDonald?
Whoa.
So,
There's a lot of, oh, wow.
Ooh.
Yeah, yeah, that's a-
I'm interested in that one.
Right now.
so your pick, Intel, Nike, Amazon, Microsoft, any damn company in US, they have to do this. Thing is, I ran into this, and then I have been giving my boss a hard time since then, and he doesn't like it that I do this. But there you go, got the good one. All right, take off the can. But honestly, 1 year to probably you're just entering the industry up to 5 years is good enough with this. After that, it is all not so good. So just be mindful of that. So you will see occasionally level 4. That I don't think is I would be concerned about level 4 be showing up here. So 1 to 5 years is typically that you should be looking at. So anything from engineer 1 to engineer 3. All right, we are 1 minute over, so. So starting today all the way to midterms, we are going to talk more or less only about transformers. We will start off with a few easy things. So today's lecture is going to be pretty easy, so don't get confused that, hey, this is going to be easy stuff.
No.
Come Monday, I'm going to discuss an operation and equivalent circuit. And honestly, that's the crux of the entire transformers that we want to talk in 347. Monday I'll be discussing 2 tests with you. One is called a short circuit test. The other is called an open circuit test. And it's so important. It shows up in your homework, shows up in your practice test. But anytime that you are working with a transformer, and if you are somehow responsible for buying a transformer or speccing a transformer, this would show up in your spec. And you need to know inside out how to do that. If you're not in this industry, just learn it because you want to get through this class. But the most important class is going to be on Monday. And voltage regulation is just a bunch of formulas, there's nothing much to it, but Monday's lecture is pretty important, so bear with me for today because I'm just starting off from scratch. And then Monday is when we hit the crux of this. And then all the way through next Monday when we sort of slow down, but it's still important if you're taking protections. And if you're taking protections class, then the CT and PT is going to be almost 1/3 of your class in protections is CTs and PTs. So we just start off nice and easy today. I think we more or less have everyone that's going to show up today. Midterm is on Wednesday, week 5. There are 4 weeks, so to say, so expect at least 4 questions. I might pop in a surprise question for you. But if you haven't looked through the midterm sample that's there, it's high time that you start looking through it. You should be able to get through 2 questions based on week 1 and week 2. There should be 1 question that week 4, Monday, like after that lecture, you should be able to start looking into it. And I think there is a sample question with, probably there's one sample question that's coming from week 5. So, yeah. All right. So,
Is the midterm going to be about 5 questions?
sorry.
Is the midterm going to be like about 5 questions?
It would either be 4 or 5. So similar to your homework problems, that's the kind of, so think of your midterm problems as, there could be 1 or 2 that's going to take probably half an hour. The rest is like, oh, I know this, it's just plug and check and get it through. So we have focused a lot on harmonics, and let me put it this way, let's not, look through the sample question paper, and that's the kind of questions that are going to show up. It's going to be similar. Don't expect that, hey, I asked for harmonics, but it is also asking for something else. It would be very easy to understand. So go through the sample question paper. I'm just breaking up because I don't want to say too much and then you go in that direction. But 4 to 5 questions. It would be number problems. I don't think I'm going to ask you any multiple choice, so it's going to be number problems. Any notes is fine as long as they are printed. No electronics other than your calculators. So, and goes without saying, on the exam day, don't come and ask me like, hey, I don't quite understand this, or how do I go about it? I just don't know how to do it. It wouldn't be fair at that point. So you are on your own on the day of exam. So yeah. Well, as long as you do your sample question papers, I don't see why you are not going to. Okay. So, show of hands, how many of you had to learn some sort of transformer during your high school, like 11th or 12th grade? You did? Okay. Just one?
Physics. AP physics.
Okay, so no one else.
That doesn't mean I'm good at it.
So I wrote a bunch of notes just to give you like why you need a transformer, what it does, and we'll get into the physics of it pretty soon. But essentially what a transformer is going to do is it's either going to step up a voltage or step down a voltage. The other thing that you need to keep in mind, and this is sort of funny, we like to throw it to the students. We keep on asking if there is something called a DC transformer, or is there a way to step up and step down a DC voltage using a transformer? You can increase or decrease a DC voltage. I'm not sure if it's part of your 300 level class, but that's called a converter.
Those are like, was it buck or boost?
Yeah.
Yeah.
So, is it TR or TER?
ER.
Okay. And then you have a buck, which means it is reducing the voltage. You have a boost, which is going to increase the voltage, and this is on DC. And then you have a buck boost, which does both depending on how you are going to configure it. I mean, there are several others, but this is how you deal with a DC. So in an AC, you are always going to use a transformer, and the location of the transformer is just going to give it a certain name. So if you are on the generator side, it's called, some like to call it a generation transformer. If you're on the transmission side, they start calling it power transformers. If you're on the distribution side, that's the, I think I have it in the lecture, but that's the sort of can that you see on the pole. With one horn and some stuff here. Sometimes there are two horns, but one horn, and this horn, it's connected to the lines. And this is on a pole. Let me just try and draw. And this is a distribution transformer, and it's called either a pole top, and some folks, because it's a can, they just call it a can transformer. The best part of a transformer is it's very cheap to transform a voltage from one level to the other using a transformer. I mean, transformers themselves are costly like $1 million. These days it's about $3 million, the big ones. But when you consider the amount of money that you save, rather than putting a new generator, you just use a bunch of transformers to step it up and step it down. There's a huge saving. And the last, and maybe we are not going to discuss in this class, but you guys probably remember that we looked at harmonics. Transformers can help you with harmonic filtering. So I have an article with me. If I have time, I'll go through it, but just sort of putting it there. Now, to understand transformers at the very basic level, it's got an iron core. So this is like this is an iron core, and on which you wind copper windings. So you put copper windings on both the sides, and you have an iron core, and then on one side you hit it with a voltage that you want to increase or decrease. And on the other side, I have shown it as a ZL or a Z load, but you will end up with a voltage that is either high or low. And we'll shortly see how the voltage is stepped up or stepped down. But the construction of a very simple transformer is that it's got an iron core and then some copper windings on both the sides. Now, keep in mind, this I'm trying to show just one phase. If it's a three-phase system, you'll have three different windings. And I believe at the very last lecture of the transformer series, we'll start seeing a three-phase transformer. Now, to start explaining a transformer, we will do what's called a first order analysis. That simply means I'm going to do a bare bone stuff. There is not going to be a whole lot of, if you are familiar with transformers, the first question is, hey, to cool a transformer, you would dip it in oil. So I don't see an oil, I don't see a fan, I don't see this and that, the protection devices. We are not going to be concerned with anything of that nature. Right now, our focus is somehow understand that I'm applying a voltage here and somehow on the other side, without any moving parts, and that's the beauty of transformer, there are actually no moving parts. You are either able to step up or step down a transformer. So to do that, we have to take what's called an ideal transformer. So an ideal transformer has mu R is infinity. Just to jog your memory, all that it means is the iron core here has such a high mu R that none of the flux escapes the iron core. So any flux that's produced by this portion remains there. The reality of it is, though, you will always have some flux leakage. And second, when you have a ferromagnetic substance, it is going to go through something called a hysteresis. And the last is, have you guys learned about magnetic domains in any of your classes? Okay. You will always have a magnetization current no matter what, and that's to manage your magnetic domains. The second assumption, and I will do sort of a highlight kind of thing at the end of this lecture, but we first looked at mu R is infinity. The second that we are going to assume is the R core has or the resistance of the core is infinite. What that means is no current actually passes through this iron core. The reality of it is there is always a small current called eddy current that's going to pass through it. But we are going to assume that the resistance is so high that my eddy current, doesn't matter what, I'm going to have zero eddy current losses. The last that I'm going to assume is that the resistance of copper is zero, which is an absolute lie. What I'm trying to do here is, I have copper winding here. I am trying to say that there is zero loss here due to copper, or a heat loss. So the formula for a heat loss is I squared R, and because it is copper, it's I squared R, this should be copper, and I'm assuming it is going to be zero. I'm also going to assume that I'm going to use very thin and long wires or coils. What that does is, by making it thin, my L, the length of my copper goes up. Sorry, by making it long, my L goes up, and by making it thin, my area actually comes down, which means my R value is going to increase. And this is a practical way that we try to design transformers. We always want to have as low resistance as possible for the copper. So keep in mind, don't get confused by this. On the iron core, I want an infinity. On the copper side, I am looking for a zero resistance. So the last I'm going to assume is when this transformation happens between P and S, P being the primary side, S being the secondary, you will soon see that I started off with a VP, but truth be told, any company that you're going to work, they're going to say the high side and the low side. High side being where there's a higher voltage, low side being the lower voltage. So for the time being, go by VP and VS. You shouldn't be surprised if you start to see H and X. So let's look through. Give me a second. All right, I was just flipping through Chapman, and they use P and S, but I think most of your homeworks would refer to H and X. H is the high side, X is the low side, and that comes from transformer data sheet where most folks just use H for the high side. Now, if you don't remember anything else about the physics of a transformer, all that you need to know is the Faraday's law. So, quick question. Have you guys seen this before, the Faraday's law, by any chance?
Looks familiar.
Familiar.
It's been a
Yep.
while.
Long while.
Yeah, not
Yes,
recently.
it's been a long time.
Okay.
Physics.
Give me a minute, I'm switching to.
Okay. Sweet stuff. File of it. Something interesting.
So remember the voltage regulation that I was talking about? This is pretty much voltage regulation, the entire formulas here. I'm looking at Maxwell. Do you see the date? Scroll past it.
There's only one result, and it's in the,
That's what it sounds like.
it's probably like in an image that is not searchable. Oh, there was a Maxwell and not Maxwell's. There you
Oh,
are.
yeah.
Okay.
So, depending on the textbooks, you are going to see this under Maxwell's equation. This is what I'm looking at. But then we end up calling it Faraday's law. Any idea why that is? You guys took EMAG, right? Both EMAGs or just one?
Oh.
Okay, in that case, it's a fair question. Shows up under Maxwell, but I'm telling you that this is Faraday's, and one of this, I believe, where do I have the age? I believe this is 0. This is enclosure. I believe this one is the Ampere's law. Yeah, this is the Ampere's law. Do you guys know the idea behind this? it has got nothing to do with this class, so I'm not going to. Okay, never mind. Try and figure it out. If not, I'll talk to you. Any idea? No? Don't care at this point?
There's so much material in this class,
No, no,
I
no,
think
no,
we're
no,
all
I know, I
worried
know.
about just focusing on that.
Maxwell's equations, why do I wanna say like gradient? Not delta.
I wouldn't call it plagiarism, but Maxwell was smart enough to add a time component to it and make it his own. So that's all about it. It is a Faraday's law. Maxwell decided to do some more research, like, play around with the formulas, and at the end of the day, it just got called Maxwell's equation. And today, if you're on the electrical side, you end up using Faraday's law. If you're on the Emacs side, you are like, what did I just do? If you're on the Emacs side, you are more on the Maxwell's equation thing. But anyhow, as I said, we were concerned with the voltage that is being produced. Turns out, Faraday's law is what is at play, and all it is saying is, if I have n number of coils, and if somehow I have a flux that is varying, so this is a varying flux, that's going to produce a voltage. Now, the way most textbooks go about defining this, and that's the reason I put it first, like if you don't want to remember anything else, this is the only stuff that I want to know, then V is equal to negative N d phi over dt. Having said that, most textbooks are going to show it using something called a flux linkage. There's not a whole lot to it. All that they're doing is putting in a lambda, which is n phi, and then taking the derivative of it and ending up with negative n d phi over dt. And here's the deal. When you have a constant flux is what happens inside a DC system, and because there is no change, there's a constant flux, and hence you cannot have a voltage change on the secondary using a constant flux, and that's the issue, that you don't have a DC transformer. So think about it this way: if I apply the same circuit, I remove an AC, I put a 5 volt DC or a 25 volt DC, all it's doing is traveling through here, and there is no flux change. It's just a constant 5 volts or a 25 that's going through here. And that's not going to create a response here. In fact, if you put a 5 volt or a 25 volt here, and if you look for a response here, you're just going to get a 0 voltage here. There's no change. And it doesn't matter how high the voltage is on the VP side. So. So the next is I'm trying to derive the relation between the primary and the secondary, or the high side and the low side. At this point, it's your choice how you want to go about this, take pictures, write notes, whatever, but I have a gut feeling, because you guys are relying on, so I saw 2 ways students are dealing it. They take pictures and then they convert it into notes, and that becomes their own notes, and it's easy to relate. Folks who are just throwing pictures at me, it's just funny at this point, because you just have a bunch of screenshots, and you haven't made your own notes with it, and you're like, oh, I don't see it. And because it was my lecture, I am literally scrolling through your pictures and telling you, hey, go back, go down. It's your money, your class, do it the way you want, but if you're not feeling comfortable with the sample question paper, I'm going to be worried. Well, not worried, I'll be concerned. Yeah. So, on the primary side, and this should be very familiar at this point. I'm going to apply an instantaneous voltage of V primary T, which is going to be root 2 Vp, that's the maximum voltage. By the way, Alan, it was not directed at you. I'm getting several emails
Oh,
and
okay.
screenshots. And I'm like, those are my screen, my notes that you just took pictures. Anyways, things that I get to see. So I'm going to apply a sinusoidal voltage on my primary side, and the flux that it's going to generate is going to be negative 1 over NP, that's the number of primary windings I have, integral of V of tau, or you can do Vt or beta, it's up to you. How I'm getting this is from my Faraday's law, where my V is negative N d phi dt, or d phi dt. So my phi is going to be what? Integral of 1 over N d. So nothing special here, it's just a moving around and getting an integral here. So when I do the integral, I end up with negative 1 over NP root 2 Vp root 2 Vp, and I'm just integrating this guy, and that gets me negative cosine omega t plus c, and an omega pops here, right? Negative and negative, they turn into a positive, and end up with root 2 Vp Now somehow your flux is dependent on omega, and what's omega? 2 pi f. So the frequency that you're operating is important. So if you're at 60 hertz for the same voltage, think about it this way, for the same voltage, at 50 hertz you're going to get a different flux than at 60 hertz. And that's kind of important. So you can't, and that's what happened in Japan. They couldn't take the same transformer and use it across the system. Like, it was, the moment they bought one from Germany and one from US, they were like, yeah, no way they're getting out of it. So this is something that you need to remember. You write your Vp equation and then you just simply derive your flux. And in general, you can write your voltage that comes out of this as, and I'm just moving things around here, not a whole lot of math here right now. Again, your flux was dependent on your frequency, which means your frequency also controls how much voltage you are generating. 348, I believe that's the project more or less. But yeah, think of it another way. If I keep my voltage constant, I can choose my frequency, and that will determine the flux. So you can think of it whatever way you want, but I have a V and I have a phi here. Now on the secondary side, we do the same jazz. I hope this arrives. So on the secondary side, we have VS, same deal, NS. All that I'm doing is I'm picking up this V from here and dropping it in here because the flux is actually shared. So what you have is root 2 VP this leads to NS. Sorry, I missed an end. This is not VS, this is NS. So NS drops from here. I can pull out my NP from here. So windings on the secondary, windings on the primary, root 2 VP. These are all constants at this point. And ddt of cosine omega t. So that leads me to a sine. And all I end up with is ns over np. Root 2 omega VP. This omega cancel. Sine omega t. I can combine this root 2 Vp sine omega t as just instantaneous of Vpt. So instantaneous voltage, and this is the And after all this jazz, the main stuff that you need to remember is anytime you have a instantaneous, that ratio would be equivalent to your RMS, and that would be equal to the number of windings of the primary divided by the number of windings on the secondary. And this, by definition, is called a turns ratio. And in high school, I learned it as N. But once I entered the industry, I've started seeing A, and all textbooks go by A. So all that you need to do, and this tells you that it is by definition. This is called a turns ratio. So the easy way to think about turns ratio is always think in terms of voltage. You need to know in terms of current, but if you remember in terms of voltage, you are golden. Primary voltage divided by the secondary voltage is always primary number of windings in the primary divided by number of windings in the secondary, and that's a turns ratio. And it's so dead cheap to transform a high voltage to a low voltage on the secondary just by manipulating the turns ratio. Can I erase this part? Yes, thanks. So for an ideal transformer, and that we are still in the ideal case, and going forward I might end up using this guy. That's how we define at several places, including I believe the textbook. We go write XFMR, which is your transformer. Some folks like to add an S just to be clear, but yeah. So for an ideal transformer, no power is lost. So P loss is 0. Essentially what I'm trying to say is my R core is infinity and my R copper is 0. And if this is true, any flux that I produced on the primary is going to show up on the secondary. This means there is no flux leakage. And if there's no flux leakage and if the power loss is 0, which means whatever power I'm producing on the input side or the high side or the primary side, that's what I'm going to get on the other side. So VP IP equals V secondary, I secondary. And we just saw what VP over VS is. So VP, VS is equal to IS over IP. And that is it. So if you want to think of in current, you need to think of it as IP. I always like to refer on the primary side and then the secondary. My turns ratio gets flipped. It's pretty simple. My thinking is always on the voltage side, because if you have seen, most of the problems are on the voltage side. Current just happens to be a sort of a output. We always control the voltage, and the way you do it is VP over VS is A. Sorry, you look at your power equation, VP IP is equal to VS IS. VP over VS is A, and if I manipulate this, you get IS over IP is equal to A. Because we always talk about ratios in terms of primary over secondary, and currents primary over secondary, so IP over IS is equal to 1 over A.
What's the is S the apparent power?
Yeah, I'm taking just the apparent power.
Okay.
Just the magnitudes. So, I asked you to look at the flux, the voltage, and then, oh, this guy is important. Sorry. In fact, from here. So this needs to be like, you just need to know it. Even if you forget the derivations, that's fine. But VP over VS is the turns ratio that needs to be somehow memorized, I would say. Same thing with this. Can I erase this or should I?
What?
Yeah.
What does A mean? If A is the
It's the turns ratio, and that simply means the number of windings on the primary over number of windings on the secondary. Isa, can I take this guy off? Oh, by the way, is it Isa or Isa?
ESA, yeah. ESA.
Missing. Hey Sierra, did you miss the second or the third lecture? One of these? Going off memory here.
It was last Monday.
Okay.
Yeah.
I'm not taking any attendance as such, but I'm keeping a track on some sort of a bandwidth thing. So far, I was asked only to take roles for 2 days, sorry, 2 weeks, so that's done. So I kind of highlighted the stuff that I really want you guys to remember no matter what. The rest is all, you like EMAG, you want to derive a few things, that's fine. Maybe it shows up on the homework. But the crux of this class is something called, at least for today's lecture, is a stuff called impedance transformation. And this is something I would say is really needed, be it your homework, be it your midterm, be it for the next class. And I'll show you the easy version of an impedance transformation right now. And once we hit the transformer, I honestly don't want to go back and discuss this again. So before next class, no matter what, just go through this impedance transformation for me. And it's a pretty simple derivation. So this technique will come into play again when we deal with per unit, your friend from last time. So if you don't understand impedance transformation, then calculating the per unit is going to be really difficult. For those of you who are kind of thinking what was per unit, it's actual value, that's the value that you have been assigned to measure or determine, divided by a base value which you guys get to choose. So impedance transformation, we will use this concept in PU. So the way to go about impedance transformation, and this is the first time that, at least for this class, we are going to do a transformer, a single phase transformer. So a round with a V or a sinusoidal means I'm applying a power supply to it. I have my primary, and I have a dot here, and I want to speak about this dot a bit. And here's my secondary winding. Here's my current on the primary. Here's my current on the secondary. And after a transformer, I have a load which needs a stepped up or a step down voltage, and I'll have my VS here. So the dot convention, it actually shows the direction of the current. So if you're on the primary side, it implies the direction into which the current flows. So into which the current flows. On the secondary side, and I purposefully left this out, it shows the current going out, here to here. This really comes into play when you are looking at three-phase transformers. For a single phase, there's a whole lot going on at this point. So a basic transformer, we looked at the dot convention, and these two lines essentially mean there is an air gap and nothing else.
There's no solid core connecting both of them, it's a gap.
For the time being, yes. Or you know what, let's go with the solid core that we discussed, it doesn't matter. Because we are looking at an ideal condition, I'm not too concerned with it. So now I'm going to define an impedance looking in from here. All that it means is I'm just going to define some sort of an impedance. This is my ideal transformer area. And what is an ideal transformer? Your R core is infinity, your R copper is 0, no flux leakage, which means any flux that I produce here shows up on the other side. So I have my Z in, that's all the impedance that I'm seeing from this side. So my Z in is VP over IP, and here's where the turns ratio comes into play. Maybe I should have the turns ratio here just for your reference. So what I'm trying to do here is anything that's on this side, like I don't know how to even solve two circuits. Like I have a voltage here, I know how to solve this part of the circuit. It's a simple wire with an inductor. But here it looks like there is no voltage source, so to say. But at the same time, somehow a voltage is showing up. So should I treat it as a load or should I treat it as a source? No real idea at this point. So through our impedance transformation, what we do is we kind of bring everything that's on this side over to this side, and thereby making our calculations much simpler. Simple comparing to keeping it as two different circuits. So VP over IP, I can relate it to my secondary using this formula. So it's ratio A, turns ratio A, times Vs, and my primary current, IP, is Is over A. And that leads me to A squared Vs over Is. And that's A squared Zn. Z in, I can even use Z in, sorry, we can even use A square to somehow connect Z in and Z out, which are literally like mechanically not connected. Like two circuits which were not even mechanically connected, there are no moving parts, and Z in turns out to be A squared Z out. And this transformation we will keep on doing over and over again, where you have two choices. As an engineer, you will always have two choices. You either bring the secondary over to the primary, or you will be taking the primary over to the secondary. And the way to do that is, what is my ZL, if I was doing the other way, is Zn over A squared. So you could go, either way, but trust me, to make your life easy, to see how it's done in the industry, try and learn one, and I would say always reflect the secondary to the primary. And the reason for that is, math-wise, physics-wise, engineering-wise, that works. Probably not engineering-wise. Math-wise and physics-wise, reflecting the primary over to the secondary works. But from an engineering perspective, you have a transformer. The primary side is where you're going to always connect voltage. The secondary is a load that it's a customer, could be another power utility. You just don't have control over it. So don't try to control something that out of bounds, always trying to bring this guy over here. So the easiest way is Z in is VP over IP. You connect the VP and the IP using the turns ratio, and then it's just algebra. In fact, I would just stop here. You can have it in your notebooks, but this is good enough. Did I talk about the dot?
Is that alpha or is that A? It's A, okay.
Now, on a transformer plate, I think I should. So the next part that I'm going to discuss is what info do you get on a transformer plate? Now, this is not the ideal transformer that I would have brought to the class, but I had this for another purpose. But it's got a decent nameplate. Any chance I can zoom in? Oh, this is great. Can you guys see this? Sort of? Okay. So this is a transformer from a manufacturer called ABB. It's got a part number. The first thing that you should see is it's got a KVA. So that's your apparent power that you keep seeing. It's got a frequency. Tells you whether it's a 3-phase or a 2-phase or a single phase. It shows an impedance of 2.9%, which means these are not true. An RCU and a ZN, there is some value to it. I believe this is temperature. Oh, yeah. 40 degrees Celsius ambient, 115 is the. I can't read that. I'm not here. But here's a big thing that you probably are not seeing from here. You have a primary and secondary. Goes using a H and an X. So the high side is H, the X is the low side. Textbooks don't do that. In fact, here's the winding. The primary or the high side is H1, H2, H3. The secondary or the low side is X1, X2, X3 with a X0. In other words, this solves a lot of issues for me. You have a delta on the high and a Y on the primary, and that's how you get rid of harmonics in one way. It introduces other issues, like there's going to be a phase shift, but there is no chance of a harmonics that happened in the delta jumping onto a Y system. The primary is stuck at 480 volts. The secondary, and that's because it's a delta, so if you take a voltmeter here, you're going to, between H2 and H3, it's going to be 480. On the primary, you get choice of two voltage. You either get a 208 or a 120. You measure any of the legs, or an X2, an X3, an X1, any one of those, with an X0, that's your neutral, you're going to get 120. But if you're measuring it between an X1 and X2, you're going to get a 208. So that's literally called out as line to line and line to neutral. And this is meant for the last class, but since it's here, you can, so imagine this. You wanted a 120, and you were thinking at 480 that's going to do the job. and for some reason you are not getting 120, you are ending up with 150. What we as a power utility would do is, we will still guarantee you the 120. What we'll do is, rather than going between jumper connections 3 and 4, we will go to either 1 and 2 or 2 and 3, so a higher voltage, thereby picking up your voltage to 120. So it's almost, okay, yeah, I could rate it here as 300 kilograms or 660 pounds, so pretty heavy stuff. And I don't want to get into this, but this is an interesting topic. All that it is telling you is DY75A. So what that is telling you is, this is the delta, this is the Y. Alright, so what does the other numbers mean?
75 amps.
No.
It's delta to Y 75A.
What are the?
View over.
So it simply means how you are able to connect these wires to get a certain connection. So remember the phase shift that I talked about? This is probably to, if you connect it this way, you probably are getting with 0 phase shift. And you can increase it by 30 degrees. But beyond the scope of this class, if I have time, I can, at some point if I have time, I'll go through that. Relay protections too is when they discuss, and I don't think they offer the class anymore. So we look through transformer nameplates, and just for the sake of, I don't think there's a homework question, but a fair enough surprising fifth question is, hey, what are the 5 things that show up on a transformer, no matter what? You know? So power transformers will always have, will show you, this wasn't a power transformer by the way, it was a smaller one. Will show you the continuous duty. It will show you the apparent power, which we saw, to some kVA. It will show you the rated frequency. And remember this, I kept on talking about how the frequency affects the phi value. So at 50 Hertz, keep in mind, I have a smaller number at the bottom. So at 50 Hertz, I'll end up getting a larger flux. Whereas at 60 Hertz, it would be a smaller flux that I'm getting. And in fact, I think I just did a simple math and it was like 20% high. And a higher flux doesn't guarantee you anything. The higher the flux, there is a chance that you're going to saturate the core. And you don't want to do that. Because if you saturate the core, the simple transformation that I was talking about here may not happen. Which means you can give primary volt and it will not give you A times Vs on the outside. Or sorry, your Vs will not, you can't predict your Vs because your saturation, the core has saturation. So the easiest way to avoid that is operate always at the given frequency. In fact, we are so paranoid about this frequency, 59 point something is good enough and 60 point something is good enough. If I see like a 58.1, we would rather shut down the grid and restart the grid.
Interesting.
Would just damage everything if it's left too long, that wrong frequency.
Not only will damage the frequency. Frequency is one thing that we just don't fool around. Yes, it will damage a lot of equipment.
Wow.
Your group, there is a person called Dr. Song. Song is his last name, I don't remember his first name. This is his bread and butter. Like, this is all he cares for. And there is something called a swing equation. And probably you're going to see that a whole lot with him. But yeah. I just drew the sketch, it's not required, but what is happening is you have a VH curve. At 60 Hertz, you're operating in the linear region. But if something was designed for 60 and you're pushing it to 50 hertz, you are actually operating in the non-linear region, and at that point, I cannot guarantee you whether the turns ratio are going to work or not. So not a whole lot, but keep in mind, power transformers, you have to be bothered by the continuous duty, you have to be bothered by the rated frequency. T max we just saw is temperature. Rated voltages at least 2. So what that means is your high and the low, but you can have many. Like in the K transformer that we saw a bunch of voltages. Rated currents, I think I have seen it in power transformers, not a whole lot in the other. And then a lot of miscellaneous stuff. This miscellaneous stuff is customer oriented. Some want it, some don't. Like the insulation type, we demand that there should be an insulation type that shows up. Most folks, nah, we don't care for it. So, kind of, I showed 6 here, rated current, maybe it shows up, so fair enough small question that can be asked. Maybe mute. So today's lecture is actually going to be very short. The reason that I kept it very short is I wasn't very sure how many of you have seen this before, and plus I want you guys to look through the notes and work yourself to have some sort of an understanding how VP over VSSA and IP over IS is the opposite. In fact, just learn this, and on an exam or once you're starting to work on your homework or at work, just remember that it's good. Oh, and don't forget this impedance transformation. That's going to drive the entire 3 lectures going forward, and I'm pretty sure the lecture on Monday is going to be pretty long, and it might even run into Tuesday. Yeah. And I don't mind taking that time for running a long lecture. So anyways, now we just saw a sort of complicated transformer configuration that I was showing that PDF. But for our purpose, let's just start off with easier configurations. Transformer. That's good. So the first one is pretty simple. It's just got one set of windings, one primary, and one secondary. Dot convention tells me current is coming into the primary, current is leaving the secondary. H1, H2, X1, X2. An example would be the next one is a multi-tap transformer. The way you do a multi-tap transformer is you have a high side where the voltage is fixed. So H1, H2, IP. Depending on the textbook, it's either an air gap or that the flux is completely linked. you have a 288 volt here. Sorry, you have a 240. Can I salvage this? Yep, I can salvage this. So you have a 240 here. And then what you do is you add or subtract a number of windings and you get your extra. So this is me trying to show that there's an extra winding here. And you get 252 volts. Or if you tap it up one winding less, you end up with 228 volts. So this should be your first example, so to say, where you're seeing that, hey, I'm able to tap up and tap down. And there's literally an equipment called a tap changer that does this for you. Could be manual or auto. If you know and if you have an understanding for the load, you would always set it in auto. What that means is, imagine rural America, you know that at a certain time, farmers are going to switch on their pumps and whatnot, and they would rather have a higher voltage than a lower voltage, and the tap changer, it just knows at a certain time of day to go up, and during night just to come down. So essentially you would be sticking it at 240, but every now and then you have to tap up or tap down. 5% is what I've seen. Probably have pictures of this, not sure. So the thing to know about this is multi-tap. I write multi-tap somewhere. Multi-tap transformers allow for manual VR. VR stands for voltage regulation, and an example for this would be 6.9 kV on the high side. So this is 6.9 kV and 240 volt plus minus 5%. Our last MECOP intern, his job was a voltage regulator. Didn't take a power class. He just completed his second year, like 200 level classes, and in 3 months we brought him to a space where he not only calculated all this, chose the equipment for me, but he also did the physical construction, which means we just gave him the foundation and he figured out the nuts, bolts, what distance should I keep it so that if there is a fault, nothing bad happens, etc. He did the entire thing. And the project, I think there was a delay in getting the transformers. It was a 10-month delay. So we were like, until the last day we were waiting, okay, hopefully the construction starts. It did not, but it was a cool project. And that was at, it was a rural place. I'm not sure if you guys have heard of a place called Gales Creek. Okay, so it was at Gales Creek. We had the same issue. There's a lot of farm there, so we have issues with voltage fluctuation, and the transformer that he had was 3-phase and it's yay big, like a water heater, but probably wider. So it's kind of cool. Like, hey, I have no understanding of what you guys are talking about. In 4 months, by the time he was done, he even did the AutoCAD, like everything that I asked him. Bill of material, physical design, and the controls. So kind of cool. So we looked at 2 configurations. By the way, this is not the entire configuration of transformers. I'm just picking the easy ones that can be discussed in this class. So you have a H1 and a H2. So I have a 480 volt on the primary. On the secondary, I actually have a choice of two voltages. So on the primary, I have a 480. On the secondary, I can either have a 240 or a 120. So the 240 happens if I tie X3 and X2 together. I end up with a 240. However, I can tie X3 with X1 and X2 with X4. So let me put it this way. If I want to get 240, and I'm just doing the secondary side, I'll have this winding. You guys, can you see this, or should I just hop into this? Alright, so I have an X1, and that winding is ending here, X2. So X1, X2. I have an X3 starting here and an X4 ending. X3, X4. So what I'm trying to say is, if I connect X3 and X2, that is short these two guys, whatever voltage is here, it's getting the full effect on both the windings, which means it will be 480 and 240. I can also do a parallel thing. So what I end up doing is, I have an X1, X2, and I'm adding, this is my X4, sort of A. X3 comes here. If I do this, I'll have an 120 volt. So you can have it either way. And this is pretty common for instrument transformers. So it's very common in instrument transformers. Instrument transformers are your CTs and BTs. Sometimes we call them PTs, and I'll tell you what those are. A CT is a current transformer. A PT is a potential transformer. But keep in mind, every now and then you are going to see BT, and every power utility is still debating whether to use a P or a B for it. And the reason is P is sort of reserved for power, and some don't like it, and it messes up their schematic drawings. So instrument transformers, there are two. One is a CT, which is current transformer. P or V, depending on how you want to go with, voltage or potential transformer. The last one that I have is a residential. Call it center tap. Oops, I'm going up. So here, I should have mentioned this. So whenever you write a primary and a secondary, the dash tells you that this is the high side, this is the low side. The X tells you that you can choose only one of these at a time. You can't have both. So it's either going to be 120 or a 240. Whereas on a center tab, and I'm telling them to be 7.2 kV, the voltages that you get are both 120 and 240. So the slash means that you're able to get both 120 or 240. So if you look between X1 and X2, you're going to get 120. Or if you look at X2 and X3, you're going to get 120. But if you look between X1 and X3, the number of windings is double, and therefore double the voltage here. So, any questions on these configurations? Yeah.
What does the current direction look like on, say, something like that?
This guy?
Yeah.
But I didn't draw the current directions because it depends on how you're going to connect it.
Okay.
But it's always so current coming in, current going out. So in fact, these two, if I'm doing a parallel connection, this is going to get connected with X1. So both of these are going to go out. And X2 and X4, it's coming out.
Okay.
Now we are sort of done for the day, but I want to jump ahead and do a three-phase transformer connections. I'm not going to discuss the ins and outs and how to figure out VP over VS and whatnot. The idea is, since you have seen a star and a delta, you have seen a YY and you have seen a you have seen a delta load as well. So I'm just going to show you how those connections work, and we will go over this at the end of transformers. But at the end of transformers, I'm probably trying to just somehow finish and complete my lectures, and maybe I may not have that kind of time then. And don't worry, it's going to be pretty quick. And honestly, at this point, I think you should all grab some sort of a writing pad or something and draw it for yourself, because it's not confusing. It's just that you haven't done it before, so that might act against you. And I need my. So I'm looking at the FE. Oh, sorry. So I'm looking at the FE handbook, and it's the same deal. They go by translation N1 over N2, and you just take the magnitudes of the voltage, or they flip the current, IS over IP, and this is your. So the FE handbook has all the formulas, but you need to know where they came from. So this is your impedance transformation that we did. What I wanted to discuss is the next page 10. It doesn't work. So if you look at the FE reference book, this is going to be a bit crazy, like, now, what's happening all over here? So at this point, I'm just going to try and see Y connection, and I'm going to do it my way, but the idea is this. You have 3 individual transformers, and you are connecting the first one, and it doesn't have to be in this order, but the first one is getting connected to the A phase of the line, the second one is getting connected to the B phase, the third one is connected to the C phase. And the neutrals, all the other end of the transformer, that's your H2, they are all tied up, and they get connected to the neutral here. So they just tied it to the second one. It doesn't matter, but what you need to know is the H2, and the H2, they are tied together and then tied to the neutral. Same deal on the primary, but this is a bit more convoluted. So I'm going to show you what I am expecting out of you from this class. And hopefully it's not too bad. So we're going to do a YY. I think it would be great if you guys also do it at the same time, so that if you make an error, you're able to see what's happening. So 3 windings, 3 sets of windings. Can you guys see this?
Yep.
So to make the transformer connection, and I have my dots here. Let's do it. So my A phase is getting connected here, and I'm going to make a distinction here by H1. This is H1. Keep in mind, these are 3 individual transformers that you are bundling up to create a 3-phase transformer. So this is my A phase, this is my B phase, this is my C phase. And all that I have to do is tie the other end, which is my H2s, together. And this is a Y on this side. Can you guys see that? Like, what just happened? So you have your A on H1, B on H1, C on H1. And I tied all the H2s, and all I have to do is either a ground or a neutral, whatever you want to call it. Any questions on this?
Is the line for H2 for A phase connected to the line of H2 for B phase?
Coming in?
H2 for the A phase, is that connected to H2 of the B phase?
Yes. So H2 here, H2. So you connect all your H2s together. So essentially what I did here is, so I connected my A phase here, B phase here, C phase here. Let me just do it in a better way. So essentially what I'm doing here is, no, I think so. So let's have this as A. This is my H1. Can you see that? H2, H1, H2, H1, H2. That was my A phase, B phase, C phase. So I'm tying up the H2s of individual transformers together, and that's how I get my wiring up this side. So same deal on the other side, no biggie at this point. But I don't remember if this is part of your homework 3 that's due on the day of midterm, but this is how you do it. This is x1, x2, x1, x2, x1. Do the neutral if I ask you to do the neutral. If not, tying it up is good enough. But if I ask you to do the neutral, you have to do the neutral. And that would show up here as and by the way, this is just one side of the transformer, it's not both. We'll have to do the other one as well. Now I want you guys to try the delta and then we are done for the day. So I'll give you like a couple of minutes. Do the same. Have 3 windings to begin with, and it's totally fair that at this point you guys are just doing the high side. But have 3 windings and try and see if you can connect it to a delta. So for those of you who didn't understand what I'm asking you to do, 3 sets of windings, connect it as a delta. And if you can do it on both the sides, else just do one side, that's fair enough. And in case it shows up on your exam, I can't talk about the homework. I'm not going to dock points if you had 5 windings here and 3 here. Just show me some squiggly lines, that's fair enough. All I want is it should look like an inductor and not a resistor or a load. That's about it. Don't get too creative.
I usually do 4. Oops.
Anyone with an answer? Yeah, you have an answer.
Yeah, so I think.
Can you show it to me?
I haven't done it, so basically it's gonna be this connect to here and this connect to here and this connect to here.
Yep. You guys need to try this. That actually looks right. I'm staring at you, man. Go ahead. Do it. Say that.
Damn, that's nice.
Oh, you're still on the Wi-Fi? Wait, where's your data? No, you need to connect the windings of the transformer so that it looks like a delta. So it becomes a delta. So I'm asking you to do the wiring. I gave you 3 transformers. I'm asking you to connect the wiring such that it looks like a delta. Yeah.
Would it be the same one?
Yes. Yep.
Hope so.
But there's just one simple correction that, uh, Isa, Mario, oh my god, who else? You, who else got it? Someone else got it. Yeah. Jasmine. So you guys got it, but the thing is, I just left the winding, so this is your H1, just make it complete. H2, H1, H2, H1, H2. All you have to do is, for those of you who are still, maybe you should use a different color.
Yeah, maybe.
And you'll repeat the same on the other side. But keep in mind, where you guys are going to struggle is, you need to bring this out. A phase. And this, yeah. So this guy, right? Do you have it? Hold on. Hold on. That's not. So H1 and H2, I'm connecting this here to my H1 over here. So this needs to come out, and it can be any one of this point. I prefer to show the center. And just show this guy. Let me try that once more. So this H1, H2 is this guy. It's connecting to H1 over here. So H2. H2 is getting connected to H1 here. I have the winding. Now this H2 is getting connected to this H1 here. So it's H1, H2. And you will do another delta the same way. So, and this kind of actually works out because the first winding, oh, by the way, did you guys get this, what I just did? So what I'm doing is 3 phases. I want to get this guy going because that's a delta connection. So this H1 and H2 is this H1 and H2. I connected the H2 of this to H1. So that's here, H2 to H1. Maybe I should write this as set 1, like first transformer, second transformer, third transformer. If so, this is my first transformer. The H2 is getting connected to the H1 here. So that's this guy. I have the winding here, so this is my second transformer. And the H2 of that is getting connected to the third one here. So H2 and H1. So this is my third transformer. And of course, you will have another set of delta on the other side, which is your low side or secondary side. Just a minute. The real trap comes into play when I have a Y delta or a delta Y. Nothing much to it. All you have to do is keep in mind that you take the delta, drop it here, you take one of the Y's here and drop it here. And keep in mind, this is your primary, this is your secondary. Here, this is your primary, this is your secondary. So just 4 connections. You learn YY and delta, and you're done. And then it's a mix and match. Isa, you had a question.
Yeah, so where are we gonna connect the neutral? Is it the secondary side?
So in a delta, there is no neutral. No neutral on a delta. How?
I mean,
So think about this, a Y system, and even in the, you have 1, 2, 3, and the joint of that is what you actually make into a neutral, right? Here you ended up, what did you end up doing? You ended up doing, H1 was connected to H2, so you lost that connection. H1 and H2 is the winding. H2 got connected to H1 here, H2 got connected to H1 here. So there's no possibility of the winding.
What about the outer sides?
Those are your phases. So here, here you will connect A phase. Here you will connect your B phase. Here you will connect your C phase. And that's this A phase. And because there is no neutral, what happens is that even if there is an issue, there's no way to pass on those harmonic issues to the secondary, and that's how we get away with harmonics in big systems. I mean, that's the cheapest way to get away with it. Alright guys, lecture's done, but yeah, go ahead.
And just to conclude, the delta figure on the left is reflected, right? But all the H's are changed to X's, right? So
Yeah.
H1.
Yeah.
Yep.
Yep.
Thank you.
So I'm still waiting on